We want to continue with our lecture. Now, we were just talking about acceleration. In this video, we want to look at a very special case of acceleration, the acceleration that an object has due to the force of gravity. In other words, if I drop something, gravity is going to pull on it and cause it to accelerate down to the ground. What is that acceleration? How does it work? That's what we want to talk about in this video. Now, it turns out that if you can ignore all the other forces but gravity, for example, air resistance, if you can ignore air resistance, the acceleration due to gravity is the same for every object. Remember we talked about the experiment proposed by Galileo of dropping the two bowling balls, one heavy and one light, from the same height, and Aristotle thought that the heavy object would hit first? It turns out all falling objects accelerate at the same rate. So a heavy object and a lighter object are both going to fall together. And so what is that rate? So basically, the acceleration due to gravity is this. An object subjected only to gravity will accelerate towards the ground. That's its direction, because remember, acceleration is a vector. It's got to have a direction. So it'll go towards the ground at a rate of 9.8 meters per second every second. That is, we can define little g, we call it little g, for the acceleration of gravity. It's so important we give it its own letter. Little g is 9.8 meters per second squared. Now, 9.8 we can round up to about 10. Now, the actual number is 9.8, but in this class, we'll very often just round that up to 10. And again, the direction is downwards, towards the ground. That is an important idea. So here's the amount, 10 meters per second squared. Here's the direction. The whole thing together is the acceleration due to gravity. But what does that mean to say that a dropped object accelerates at 10 meters per second squared downward? Again, what it means is that the velocity increases by 10 meters per second every second. So if you remember, we can write it out like this. 10 meters per second squared equals 10 meters per second every second. So here's an image of somebody, they've dropped a ball or something off of a tall cliff, and you can see every tick of the clock, the ball is traveling further and further. That means it's going faster and faster. So at 1 second, what's its speed? Its speed is going to be 10 meters per second. At 2 seconds, what's its speed? It'll be 20 meters per second. Then after 3 seconds, what's it going to be? It'll be 30 meters per second at 3 seconds. So this is the idea. It's telling you how the velocity is changing when something is dropped, and every second the speed increases by 10 meters per second. So the acceleration, again, 10 meters per second squared. And of course we know really it's 9.8, but we're going to round it up to 10 to make our lives easier. The next thing that we want to look at is the distance formula. And so what we have for the distance formula, and this, by the way, is for a dropped object, specifically an object that's been dropped from rest. So I'm holding an object up above the ground, I let it go. When it leaves my hand, it hasn't started moving yet, so it's dropped from rest. It's got an initial velocity of 0, but as it falls, it's going to speed up and speed up. It's also going to travel further and further. So how far will it travel? This is the formula that we can use. Now, this g is, again, that's our acceleration due to gravity. And technically it's 9.8, but we're just going to call it 10 meters per second squared. And d is, of course, the distance. And then t is the time. And so we can plug those values into our formula to tell how far something falls or how long it takes to fall a certain distance. Let's look at some examples with this. So here's an example. We have an object is dropped from rest. That means its initial velocity is 0, and we can use our formula from the previous slide. So it's dropped from rest off of a tall bridge if it takes 6 seconds to hit the ground below, how high above the ground is the bridge? Well, we can simply apply our formula. We know that d is equal to 1/2 gt squared. And by the way, when people make a mistake with this kind of a problem, usually they forget about that squared. Remember, t squared just means t times itself. And so we can plug all these values into our formula and say this is equal to 1/2 about 10 meters per second squared, and then times t, which we're told in the problem is 6 seconds squared. If I multiply all this out, I get 1/2 times 10 gives me 5. That's 5 meters per second squared, times 6 squared gives me 36 seconds squared. And so I can now multiply 5 meters per second squared times 36 squared, 36 seconds squared. And notice I've got seconds squared here, I've got divided by seconds squared there. So the seconds all cancel and I'm left with units of meters for my distance, which makes sense. That distance could be in meters. But what is 5 times 36? I honestly don't know, but if I plug it into my calculator, it tells me that the distance works out to be 180 meters. And so that is how high the bridge is above the ground, 180 meters up. Now let's look at another example. This one is using the same formula, but it's a little bit different of an example. It says an object is dropped from rest off of a 20-meter tall cliff. So in the previous example, we didn't know how tall it was, but we knew how long it took. Here the question is, how long does it take to hit the ground below? But no worries, we can just use our same formula. We can say that d is equal to 1/2 gt squared, and what we're trying to find is this value t. Now I'm going to go ahead and plug in the numbers. I've got 20 meters is equal to 1/2 times 10 meters per second squared times t squared. And if I simplify that, I get, what I'll do to simplify, I want to get t by itself. And so if I multiply both sides by 2, I'll get rid of that 1/2. And if I divide both sides by 10, I'll get rid of that 10, and I'll have t left by itself. And so if I write all that out neatly, I get 2 times 20 meters divided by 10 meters over seconds squared. And so multiplying all this out, I end up with that t squared is equal to 4 seconds squared. So I've got 2 times 20. 2 times 20 gives me 40, and then I divide by 10, and that gives me 40 divided by 10 leaves me with 4. And then here I've got the meters cancel. 1 over seconds squared. So the seconds squareds come up top. And I am left with t squared is 4 seconds squared. Now we don't want t squared. What do we want? We want t. So to get rid of t, I just take the square root of both sides, and I end up with my answer that t is equal to 2 seconds. And that's how long it takes for it to fall 20 meters. Now here's a figure from your textbook, and it's very useful to look at this because it pulls together a lot of the things we've been talking about. So this guy throws this ball at the edge of a cliff, and he throws it straight up. And so the ball goes straight up, but it's slowing down on the way up. It stops at the top because in order to turn around, it momentarily stops. This is just like the example that we did of throwing the ball into the wind, if you remember that one. And then it moves in the opposite direction, and it's speeding up. Now, which way is the acceleration pointing? The acceleration due to gravity is always pointing down towards the ground. So when the object is moving upward, the velocity is up, the acceleration is down, we know that that means it's going to be slowing down on the way up. And it's eventually going to slow down so much that it gets to zero. Then gravity is going to keep pulling it down, keep accelerating it towards the ground, and so it's going to speed up on the way down. And in fact, we know how much the velocity changes every second. It's a 10 meter per second change every second. So here we start out, we threw it, it's at 30. After 1 second, it's going 20 meters per second, 10 meters per second, 0 meters per second. That means at 3 seconds, it stopped at the top momentarily. At 4 seconds, it's going negative 10 meters per second. In other words, 10 meters per second downward. At 5 seconds, it's got another 20 meter per second another 10 meter per second velocity change, leaving it at 20 meters per second. And then another 10 meter per second velocity change, it's going 30 meters per second. Again, that negative means it's going down. 40 meters per second in the negative direction, and so on. And so this is a really useful picture. And if you understand all of this, and you understand a lot about what we've been talking about. Incidentally, by counting the number of velocity changes, you can also count how many seconds have passed. And so if it didn't say here that it was 6 seconds, and I asked you, how long does it take to get back to where it started height-wise? Well, you could just count. That's 1 velocity change, 2 velocity changes, 3, 4, 5, 6. That's 6 seconds. Easy peasy.